There's this beautifully simple idea that's, well, kind of hiding in plain sight inside almost every piece of software you use. It's called a finite automaton, and it's basically the hidden engine that powers digital pattern matching. Have you ever used Find and Page in your browser and just wondered how it can scan a massive document in like a split second? Or maybe how your code editor instantly knows you've made a typo? It really does feel like magic, doesn't it? But it's not. It's actually a really elegant and incredibly efficient method for matching patterns. At the end of the day, the computer is really just following a map, a very, very specific kind of map that's designed to do just one thing and do it perfectly. Figure out if a sequence of characters matches a pattern it was told to look for. So, that map, it has a more formal name, a finite automaton. Sometimes you'll hear it called a finite state machine. Now, I know that sounds a little intimidating, but the core idea is wonderfully simple. So let's break down what that really means. Okay, so a finite automaton is basically a model of a machine, right? It takes a string of characters as its input. Could be a word, a number, a line of code, you name it. And its whole job is to figure out if that string follows a very specific set of rules. It gives a simple answer. Either, yep, that's a match, or nope, it's not. And this diagram here shows us the two basic building blocks. The circles are called states. You can just think of them as different locations on our map. And the arrows, those are the transitions. They're the paths you take to get from one location to another. And the path you take is decided by the character you're reading at that moment. Let's look just a little closer at these parts. So you've got your states, which are kind of like stages in the process. You've got your transitions, which are the rules for hopping between them. And then there are two special types of states. There's always one single start state, that's our entry point. And then there can be one or more accepting states. Those are the ones, often shown with a double circle, that signal a successful match. That's our destination. Okay, so theory is one thing, but let's actually make this real. We're going to follow along as a machine reads a simple string step by step and see exactly how it decides if the pattern is a match or not. For our example, we're going to feed our machine the string xcomp. Now, this particular machine is built to recognize valid variable names, or identifiers, in a programming language. You know, the kind of names that have to start with a letter and can then be followed by more letters or numbers? All right, so here we go. The process always kicks off at the start state, which for us is state 1. The very first character the machine sees from our input string is the letter X. Now, the machine checks its rulebook. From its current location, state 1, it sees an arrow, a transition, labeled letter. Well, X is a letter, so it does what the map says. It follows that arrow and moves over to state 2. Simple as that. And this is where it gets really efficient. The machine now reads the next character, C. It looks at the rules from its new location, state 2. And what does it see? It sees an arrow labeled letter that just loops right back to where it already is, back to state 2. So for the C, the O, the M, and the P, it just keeps taking that loop, one character at a time, staying right in state 2. So after that final P, we're at the end of the input. And where did the machine end up? It's in state 2. And because state 2 has that special double circle, we know it's an accepting state. And that means the pattern is a match. Success. So that last example was really straightforward, right? For any state and any input character, there was only one possible path to take. But what if there were choices? This actually brings us to the two main flavors of these machines. The machine we just used was a deterministic finite automaton, or a DFA for short. It's deterministic because its path is completely set in stone. There are no choices, no ambiguity at all. On the flip side, you have a non-deterministic finite automaton, or an NFA, and these are more flexible. From one state, a single input might give you a few different places to go. It's kind of like exploring multiple paths at the same time. So here you can see two different machines that actually do the exact same job. The NFA on the left is often way more compact, and honestly, it's easier for a person to come up with the design. The DFA on the right looks more complicated, but it's a direct, step-by-step algorithm a computer can run super efficiently. But here's the really cool part. Any NFA, no matter how wild it looks, can be automatically converted into a DFA that recognizes the exact same patterns. So why are we talking about any of this? Why does it matter? Well, this simple little model of states and transitions, it's not just some abstract idea from a textbook. It's a fundamental tool in computer science that's used in incredibly practical ways every single day. Every single time a compiler looks at your code, the very first thing it does, a step called lexical analysis, it uses a finite automaton to chop up your code into meaningful pieces. Remember that find feature we talked about? Yep, that's powered by this. Even things like network devices checking commands or the actual design of computer chips, all of them rely on the principles of these simple state machines. They are everywhere. There's this quote from a classic computer science book that I think just captures this perfectly. A finite automaton is one of those few basic ideas that becomes the foundation for building these incredibly powerful, complex tools. It's such a beautiful example of how simplicity can lead to immense power. And really, that's the thing to take away from all this. At the heart of a task that seems so complex, like a computer understanding language, there can be a simple, elegant map of states and rules. It kind of makes you wonder, doesn't it? What other big, complicated problems out there could be solved just by sitting down and drawing a few circles and arrows? Thanks for spending this time with me.